I am Julius Sumner Miller. I teach physics. Consider this astonishing thing. I have here a flat-sided whiskey bottle, now filled nearly full with water. And I say the following regarding it. If it were filled completely with water and provided with a tight-fitting screw cap, I could then use it as a hammer with which to drive this nail into this block of wood with absolute abandon and freedom. And we are led to ask, why is it so?
Professor Julian Miller, a visiting American physicist, has more fascinating demonstrations of physics for you and more problems, naturally. I think,
Hello,
Professor
Bob.
Miller,
How are you?
again, why is it so? How can you get away with that?
Isn't this amazing? Water, you know, has fantastic properties, unbelievable, beyond human imagination. You couldn't think of what it possesses. Indeed, more marvelous than the human mind can conjure up. My purpose here is to show one property, that it is highly incompressible. Furthermore, that glass is highly elastic. So what do I have? I have a flat-sided whiskey bottle with which, the original contents gone. I have now filled the bottle, not quite full with water. Do you see there's a bubble there?
Yes, yes.
And this is bad for my purpose. But if the bottle were filled completely, this could be done by warming the water gently and driving out the occluded gases, then filling this gently and full. Further, instead of a cork stopper, which I have, I would have a tight-fitting screw cap. So then we have a flask full of water, and water is nearly incompressible. I could then use this to drive that nail using this as a sledgehammer. Isn't that amazing? Hard to believe,
Again,
isn't it?
why is it so? Because
Why? Well, the glass is highly elastic. The glass would yield a little bit under the forces imposed on it, and the whole business would move a little upward by virtue of this contact force, but the water inside would suffer no compression. Then after the deformation by the glass here and here, things would recover and be themselves again.
we imagine glass to be brittle and fragile.
But it's highly elastic. You see, this idea of elasticity is badly misunderstood. Steel is highly elastic. Glass is highly elastic. Rubber is highly inelastic. So what do we mean by elastic? If a stuff is elastic, it recovers after being deformed.
Yes.
So steel suffers some deformation but recovers. A good spring suffers some deformation and then recovers. We say it's elastic. But a rubber is not highly elastic. Indeed, if you took a rubber band, those we call elastic bands, and measured a new one, let us say it is 2 inches long, then stretched it but once and measured it again, we'd find it more than 2 inches long.
So it hasn't recovered.
It hasn't recovered.
Yes. And can we re-emphasize one point? I think to save people from trying this at home, you said that you must heat the...
Warm the water gently to drive out the gases which are locked up in it. Then fill it ever so gently and provide it with a screw cap so that things are tight. You see, this would only pop out if I kept banging it here.
Yes.
Because it's only a tight fitting.
So you need almost a wax fitting over it.
Right. Now then, I warn people against, prudence must be exercised here. People can get cut badly if they don't do this with judgment.
Yes.
But what I'm saying is this. Isn't it fantastic that water should have this property? See,
is.
solid like a hammer. Let me prove to you by another demonstration that it is nearly so. Here I have another flat-sided whiskey bottle. Do you see the role that empty whiskey bottles play in my
It
life?
does seem to be quite important.
Oh, yes. Let me tell you how I get them. I need dozens of them because sometimes these experiments, as one says, do not work, and so they break. Now, for years I had a little dog, and I would walk in the morning, 4 o'clock or so, or 5, with my little dog to vacant lots and city dumps and collect whiskey bottles. But then after a few years, you see, when my face got known, I could no longer hide, and to avoid being identified, I gave up that practice.
Well, how do you get them now?
How? I send my wife on this errand. Isn't that a enchanting little tale? So consider here. Here is a flat-sided whiskey bottle. It's fitted with a tight-hole stopper. And here is the height of the water in a tight-fitting tube. Now, what am I going to do? I am going to squeeze this flask ever so gently on the walls with my fingers.
Yes.
Not much to that, really, but watch the drama of it. Watch the water in the tube. Do you see the water go up?
Yes.
Yes. Now you do it. I'll hold it. Take the bottle in both hands, if you wish, so it doesn't joggle. Notice that. Notice that. Now, do you see that when you squeeze and drive the water up and then let loose of the squeeze, doesn't the water come down?
It does.
Doesn't that mean that the glass came back to where it was?
So the glass is elastic?
Glass is elastic. Question. Hold that right there so we get a view of the level of the water. Supposing I turn the flask the other way, we'd like to get a shot of the whole glass, and I squeeze on the narrow sides.
Yes.
What would you predict regarding the level of the liquid in the tube?
Will it move less because it's...
Want to try it again? Remember, when I squeezed the wide sides, the liquid went up. That's clearly because I made smaller the volume of the bottle, caving in the sides, so to speak. What's going to happen when I...
You make the volume of the bottle larger.
And so?
The water drops.
Right. You see how wonderful it is to think the thing out and come to the right solution on your own. Isn't it a satisfaction?
I was well led.
Oh, well, no. Watch the level now of the liquid. I'm going to squeeze the narrow sides. Watch it.
Yes. Yes. Down first.
It goes down first.
Yes.
Yes. A wonderful little exercise.
Fascinating.
Indeed. I want to tell you more about this one. Some years ago, I wrote a paper on this, examined it a little more severely, and a Yugoslav physicist at Ljubljana, the famous Yugoslav university, took that little paper that I wrote and expanded it to 40 pages of abstruse problem and physics. And this paper was sent to me, but I couldn't read it because it was in a tongue I could not read. So I went to the Yugoslav consul, and he said he couldn't read it either because it was in Croatian, 3 languages in Yugoslavia. So he sent me to a lady who could read it. And she served me a Croatian dinner, and her husband played me some Serbian music. All out of a little problem concerning a whiskey flask. Isn't that an enchanting little thing? One more. The classical problem of the Cartesian diver. Now, if we get a close look at that, you see that there is a little medicine vial in there, in which some water resides part way up. The flask inside open at the bottom and closed at the top. See it?
Yes.
I'm going to draw the picture on the board. Watch it. We have a little flask inside, such as medicine would come in, and this resides in a taller flask like this, in which water resides. And you see that the water level is about right there in the big flask, and the water level inside is about right there. So are you not agreed that this is the picture we have on the table?
Yes.
Now across the top of this is a little rubber sheet. And now what am I going to do? Clearly there is air in here, and there is air in here, and this business is where it is for the following reason. First, there are some forces down on it, and there are some forces up on it. The forces down on it are the weight of the flask, the weight of the water in it, and the weight of the air in it. The forces up are Archimedean, the buoyant forces due to Archimedes' principle. Now what am I going to do? I'm going to push down ever so slightly on this rubber sheet, ever so slightly. When I do that, will not the air in here suffer some compression?
Yes.
Now Pascal, Blaise Pascal, 17th, 18th century. You should read about him. One of the greatest intellects in all of human history. In fact, possessed, I suppose, of at least 7-fold immortality. A poet, a writer, a physicist, a mathematician, a philosopher, a fanatic. Mad, absolutely, but left us a wilderness of important things. I'm going to push down. The air gets compressed. Pascal said, what I do here is felt throughout the system without diminution. The air in here gets compressed. Some more water rushes in. The system gets heavier. And what must it do?
It sinks.
It sinks. Then I let go here, and the converse process operates, and up it comes. And this is exactly like submarines work. Come watch it. Watch. Watch it now. Watch it. Watch the water level in him,
Yes.
and watch him go down when I push. I'm going to push. Do you see him go down?
Mm.
Isn't that pretty? Do you see him come up when I have let go up here? And so we can control his motion. I can push him part way down if you wish.
And hold him there.
And hold him there. There it is. Notice. Notice. He's about 2 inches submerged. Isn't this a beautiful little thing? Now, I am showing this for the following reason. When I use this in my lectures and ask this question, does the air in him help to buoy him up? B-U-O-Y. The answer in chorus usually is yes. But I wish to correct this false notion. Are you not agreed that the air inside of him has weight?
Yes.
And hence that force can act only down. And so those young observers who are watching us here must remember when this exercise comes in their physics career, never to answer the question this bad way. You see, the air in him doesn't buoy him up. It is only the water outside that buoys him up. You got it? Only the water outside. It is quite like another question. Why do we blow up a balloon? You know, you want to go aloft in a balloon. Why do you blow it up? Because the gas inside the balloon lifts the balloon? No! You simply blow up the balloon to distend it so it displaces a lot of atmosphere, so the atmosphere lifts it up by Archimedes. Got it?
Mm.
Okay, you got it? Now, so much for that. Oh, yes, this is a question. Have we done this? No, we haven't
no.
done it. Question. A round flask, 1-hole tight stopper with a tube fixed and the level of the liquid right here. This is to be likened to Galileo's thermometer. Galileo's.
Thermometer.
Right, thermometer. I want to ask the following. Supposing I picked up this flask as it now stands, it is filled with colored water so we can see it clearly. Supposing I picked up this flask and put it in a great big pot of boiling water. That is, I just submerge it so far in a pot of boiling water. Question, what is the very first thing we would see happen here? Don't answer, don't answer. Have I made the question clear?
You have.
I pick this up and put it in a pot of water. Question, what happens to this level? What do we see first? This question will be answered next time.
I think I have the answer, but I'm obviously wrong.
Tell me privately. Let me say to you with undue boldness, you are wrong. Does that make you happy?
We'll see what the...
All right, good. Next question, next problem. The problem of the double bubble. Do you like that title?
Do you want to demonstrate this beforehand?
Yes, on the blackboard. The case of the double bubble. Yes, erase that for me, will you? Yes. The case of the double bubble. Here's what I have. I have a glass T-tube, which is turned down a little like that. And to the upper part of the T-tube is a rubber tube, whose purpose will be known in a moment. And then you see, connected to the lower ends of this rubber tubing are 2 little funnels. Do you see how exact I have the picture?
Yes.
All right, 2
Yes.
funnels. Now I am going to dip these funnels into a little saucer of soap solution, and I am going to blow some bubbles. Do you see what has become of me in my later years? Blowing bubbles. But bubbles, Mr. Sanders, have strange and dramatic properties. And indeed, I invite the young people to read a book by C.V. Boys, just like boys and girls, entitled Soap Bubbles. A man spent his lifetime exploring soap bubbles.
I've heard of it.
Yeah, beautiful thing. Now, I blow bubbles. Now, I could blow 2 bubbles which are the same size, and there would be no problem. So I have no interest in that. Do you see? I have interest in doing those things which what? Raise problems. I'm going to blow 2 bubbles. One, let us say, a small bubble, and one, a big one. Do you see I can do that? I can do that. I can do that in the following way. I blow some air through here by my mouth, and when this bubble gets so big, I pinch off the rubber tube here, and we'll let that put more air in here, right?
Yes.
Now, having blown the two bubbles, a big one and a small one, I shut off this over here. You know? I shut it off, that is, I pinch off that tubing.
Yes.
Are you not agreed that these bubbles then have connection with each other, but not with the outside air?
Yes.
And the question, obviously, is obvious. What is the question? What will happen?
What happens to the bubbles?
Right. What happens to the bubbles? What would you say?
Will they equalize or?
Notice, don't ask me in turn, what do you think the bubbles will do? Doesn't reason and logic and sense dictate that they will get equal? Good.
I bet it doesn't happen.
Well, let me blow the bubbles and leave this as a question to be answered next time. Let me blow the bubbles. Watch it now, just to show that I can do it. Uh-oh. It'll take a moment, I think. We need a little more soap. Solution. Now I'm going to blow a bubble there. Do you have one there?
Yes.
Now I'm going to show you that I could blow a small one here and a big one there.
Whoop, whoop, lost him.
Yes, thank you. So I'll blow a small one here. Uh-oh. We're having, I think there's a little blow in the studio. That's good enough. Are we not agreed that we have a small one and a big one? Right? But I am going to get rid of them.
I was
Why?
just about to pinch this to find out.
Do you see that this is an enchanting problem? Let me remind you, I have blown more air into this one to make it bigger, and I have left this one small. We shut off the connection with the outside air. They are connected with each other. Question, what do we now see happen? Isn't that an enchanting little inquiry?
And we have to wait until next week.
Next week.
Now, I'm intrigued. You've written up here the problem of Pascal's paradox.
Oh, yes, Pascal's paradox. Yes. But before we go to that, let me dispose of the questions from last week. Hadn't we better do that?
Yes.
Remember what we asked? The case of the good and the bad egg. We have in the refrigerator an assemblage of eggs. They have been gathered there over days and weeks, and we are now worried. Some may be bad and some may still be good. How shall we separate them? Was not that the problem? Did you propose a solution? I haven't heard it.
I think I tried to suggest by spinning the same as.
But this will not be so successful. This will not be definitive evidence. It may tell you something, but not too well. Solution. You put them in a great big vessel of water. Now, some will be seen to sink, and some will be seen not to sink. And the question then arises, which have sunk, the good ones or the bad ones, or which have not sunk? Do you see, the question is still unanswered, and so I think I will leave this one for next week.
As long as you remember to answer it, that's
Right.
the main thing.
Which reminds me of the old lady who did this very same thing, and in fretful dilemma, not knowing whether it was the good ones that sank or the bad ones, she threw them all out. But I have suggested the solution. I ask now a next question. Some sink and some do not sink. Which is which? Do you see my method of instruction?
I do, yes.
I do not wish to provide too much crutches for the intellectual process. You feed only a little, invite curiosity, and those who wish to know will go and seek it out.
I feel a bit like a donkey being led by a carrot there.
Oh, like that. All right. The case of the good and the bad egg, we must then return to. You will remind me. The next one. I asked you concerning manhole covers. You know, you look on the street, and here is a manhole hole, and there is a cover that fits it, and the cover is round.
I had no idea why.
Suggest a point of view.
Well, I tried to last week, and I don't think I got very far.
Well, one answer would be something about, the stresses and the strains, easier to make. The answer is trivial. Some say, that's because the holes, they fit around, Julius. Don't you like that one? The answer is this. This is the only hole, shape, for which one cover fits and cannot fall in. Supposing the hole were square, and you had now a square cover, and inadvertently put the cover down along a diagonal, wouldn't it fall in?
Well, it could.
Right. Do you see that this one cannot?
Yes.
And it fits in any direction it is put down at.
Such an obvious answer.
Yes. I have one more question while we're on the shape of manhole covers. Do you see the kinds of questions I ask? I wish these questions to stir some thinking. Next time you are on the street, look at a hydrant that the fire people use, the fire department. The hydrant has a very special shaped nut on the top. Do you know what shape it is?
No, you better answer that.
Yes, I'll tell you. 1, 2, 3, 4, 5. It is a 5-sided nut on the very top. Having told you this much, I would ask you, why is it this shape?
Perhaps they only have the spanners they use as a key. Nobody else can have the right fitting spanner to get at the...
Very good. Do you see that it calls for a special wrench? One of our ordinary wrenches could not do it because one jaw would fit here and the other would be on a point. And one jaw would fit here and the other would be on a point. And so for all sides and points. But do you see again what I'm trying to emphasize? Observation. Look at it.
Yes, yes. Well, I've been observing something for several weeks now, and that is a contraption of yours out here with ping-pong balls and bits of string.
Yep. Does not this look like a device from Leonardo? A device with which to sack cities? Yeah, this device.
People haven't seen it yet. Perhaps you could draw it.
Here it is. Do you remember a few days ago, we considered two bodies falling from rest, an enormous, massive one,
yes,
and a small, tiny one? And I said they fall at the same rate? You remember that?
Yes.
Good. Now I wish to consider some more projectile motion, or falling bodies. We have there an apparatus that does this. Here are two identical bodies, which are ping-pong balls in this case. We have a mechanism that releases one to fall freely to the ground. See, this one is going to fall freely. At this very instant, this one is projected this way so as to take this path. You see? Just like firing a bullet, which would go down eventually. Question. How do their times of flight compare? This one falls freely, and this one goes so. How do they compare?
Well, presumably this one would take longer. It's traveling a greater distance.
Yes,
but then again,
yes.
it might be traveling faster.
Oh, yes. Well, here is an interesting thing. And for its first answer, we must go to Galileo, that great giant, you know, who incidentally died the very year that Newton was born. Galileo Galilei. And I visited his hometown, and I visited his tomb in Florence. Beautiful thing, stirred me to weeping. Now, I'm going to show you that they reached the ground in the same time.
Let's have a look.
And Galileo showed this. More than that. The drama and beauty in this stirred the mathematicians of that day. Come and see it. How's our time? I have no idea.
Well, I think we're running a bit short of time.
Are we?
Probably about 7 or 8 minutes left.
All right. Now watch. Look here. Do you see what I have? I have a mechanism that's going to throw this ball that way, and I have, at the same time, this one released here. Do you see? This looks like a device from Leonardo. Yeah, a device. We could sack cities with it. Now watch. This one goes, and this one drops. Watch it now. And we have to see exactly and rely on our senses, sight and hearing. Get it? Did they not? Arrive at the ground at the same time. Indeed, let's try it once more. And are you not astonished at this event?
Let's just see it once again.
Once more, right? Yes, arrived at the same time.
Thanks.
I say, Mr. Sanders, that this is a very dramatic thing. Would you not expect young people to be enchanted by this? Now I must ask them, why is this so? With which we will not be concerned now.
Let's come on to our next one. We have 5 minutes.
Yes. Now, that one with the disc, with the rolling wheel, will take me 7 or 8 minutes to talk, and so we will not go to it. Let me show you some other more interesting things that are shorter in discourse. First, we have here 2 metal plates. How big are they? Notice how big they are. About as big as my fingers, so. Good?
Yes.
Now they are ground smoothly on the face, and I can put them, see, pretty smooth, and I can put them together like that. Now, I am going to improve things by putting a drop of water between their faces. Notice I pour a little water. Good. Do you see there's a little water there?
Yes, very
Let
little.
the camera get that. Oh, he's done very well. A little water. Now I'm going to bring the other plate down on top and squash out the drop of water. Spread it out. The plates then are fitted firmly together, and I invite you to pull them apart at right angles to their faces. Gently, gently. No, you're pulling too hard.
Oh, sorry.
Now, lap them again. Now, okay, gently. Yes, yes. Is there not a substantial force there?
There is.
Yes. Now, why do I show that experiment? Of all the people who have contributed to physics and our knowledge of the world, who must be held in the highest repute?
Newton.
Newton. Newton said this: the parts of all homogeneal, that was his word, the parts of all homogeneal bodies are held together very strongly. I wanted to demonstrate this. So, this water between gives rise to some forces called surface tension, the nature of which we do not know. But when one does the mathematics for these two plates, it comes out like this, that the force required to pull them apart is given by an expression of this sort, which I will speak of briefly. A is the area of the plates. T is the surface tension of the water, and little t is the thickness of the water film between the plates. Now we ask, Mr. Sanders, how thin can that water film be? Well, isn't it clear that the thinnest water film we could have would be 1 molecular layer thick, right? 1 molecule. If that water layer is 1 molecule thick, how great do you think the force is to pull these apart? How great? 1 pound, 10 pounds, 100 pounds? What do you think?
By the feel of it, several pounds.
Yes,
anyway.
yes. Well, if we could actually get that monomolecular thickness of water, the force to pull these two plates apart would be 100 tons. Do you see what a strange and dramatic thing the world is? Isn't it fantastic? Next.
You must be fascinated in your own life, too, going around with these kind of things in your head.
Well, don't you
constantly.
see? They have added to my life with a fullness unbelievable. Why? Only because you get curious, and curiosity begets itself, and soon you are diseased with curiosity. But see how full the life can be. And my ambition is what? To raise the young ones from the earliest years in this same kind of intellectual gymnastic, so that when they look, they see, and when they listen, they hear. Do you see the necessity for that? One more question. One
Professor,
more.
we have 1 minute.
1
the
minute.
program.
All right, here we are. Here is an old experiment. The ball and the ring. Here is a ring. Here is a ball. The ball doesn't go through the ring. So what do? We heat the ring. Then you know that the ball goes through, right? Now everybody says, yes, I've seen that and I understand it. Well, you know, understanding is hard to come by. Few have it. If they understand that, then I wish to explore the following. I have here a metal plate with a hole in it. You see that little hole? There we are. There's the camera, gets the hole. I ask you this. This is a big plate with a tiny hole. Here, indeed, is another plate. Do you see this has a tiny, tiny hole? Do you see that? Can we get that?
There,
Yes,
yes,
there it is. Tiny hole in that plate. I ask you, supposing I heated this plate uniformly, couldn't I do it by putting it in an oven? What happens to the hole? Tiny hole in a big plate.
Shall I answer it?
No. This is for next time also. But propose your answer quickly.
No, I won't.
All right.
Thank you very much again, Professor Miller, and another program next week.
Thank you very much.
Thank you.
Bob.